continue with our lesson on mathematical induction. Recall that from the first part of the video on mathematical induction, we showed that to prove by mathematical induction, we only need to show three things. Firstly, we showed that the statement is true for n equals to 1, and then we showed that we assume that it is true for n equals k, and then we now check that it is true for n equal to k plus 1. We now give more examples on how to prove by induction. Prove that this guy is an integer multiple of 8. So we show for n equals 1. So for n equals to 1, we have 3 raised to power 2 times 1 minus 1, which is equal to 3 raised to power 2 minus 1, which equals 9 minus 1, which is equal to 8. And 8 is a multiple of 8. So it is true for n equals 1. And then we assume that it is true for n equals k. That is 3 raised to power 2k minus 1 equals to 8l for some integer l. Let's explain this l part. For instance, if 10 is a multiple of 2, it means that 10 equals to 2l for some integer l. And in this particular case, my L is 5. So 10 equals to 2 times 5. So if we are assuming that this guy is an integer multiple of 8, so this guy equals 8L for some integer L. So we can call this equation star. Now we check that it is true for n equals k plus 1. That is, we have 3 raised to power 2k plus 1 minus 1. Now this is equal to 3 raised to power 2k plus 2 minus 1, which is equal to 3 raised to power 2 times 3 raised to power 2k minus 1. This is by the law of indices, which is equal to, this is 9. Now, from equation star, 3 raised to power 2k equals to 8l plus 1. So we can substitute that. So 3 raised to power 2k equals 8l plus 1 from our assumption star minus 1. Now this is equal to 9 times 8l plus 9 minus 1, and this equals 9 times 8l plus 8. So we can factor out 8, and we have 8 into brackets 9l plus 1. So we see that this guy is a multiple of 8. And so it is true for n equals to k plus 1. And so by the principle of mathematical induction, this expression is an integer multiple of 8 for all natural numbers n. And finally, we prove that this guy is divisible by 64. So for n equals to 1, we have 3 raised to power 2 times 1 plus 2 minus 8 times 1 minus 9, which is equal to 3 raised to power 2 plus 2 minus 8 minus 9, which equals 3 raised to power 4 minus 17, which is equal to 81 minus 17, and that gives us 64. So 64 is divisible by 64, and so the statement is true for n equals 1. Now we assume that it is true for n equals k, that is 3 raised to power 2k plus 2 minus 8k minus 9 equals to 64L for some integer L. Now we can call that equation star. Then we now go ahead to show that it is true for n equals to k plus 1. So we have 3 raised to power 2k plus 1 plus 2. That is, we are substituting n for k into this expression. So we have this minus 8k plus 1 minus 9, and that gives us 3 raised to power 2 times 3 raised to power 2k plus 1 by the law of indices, minus 8k plus 1 minus 9. And this gives us 9 times 3 raised to power 2k plus 2 minus, if we open this bracket, we have 8k minus 8 minus 9. And that is equal to 9. Now, by our assumption star, from our assumption star, 3 raised to power 2k plus 2 is equal to 64L plus 8k plus 9. That's from the assumption star. So we can substitute that for this here. So we have 64L plus 8k plus 9. That is from this assumption that we made earlier. Now minus 8k minus 8 minus 9 gives us minus 17, which is equal to, we can open up this bracket. We have 9 times 64L plus 9 times 8k, that's 72k, plus 9 times 9 gives us 81, minus 8k minus 17. Now this is equal to 9 times 64L plus 72k minus 8k gives us 64k, plus 81 minus 17 gives us 64. And this is equal to, we can factor out 64. We have 9L here. 64 in 64k gives us k, plus 64 in 64 gives us 1. So this guy is divisible by 64. And so it is true for n equals to k plus 1. And so by the principle of mathematical induction, this statement is divisible by 64 for all natural numbers n. I hope you enjoyed this video. If you have any question, you can drop them in the comments section. Thank you.